So now this is where we stop. The sums random variable will give you so it's like kind of very fundamental idea that if you have a sum of two random variables, then the density is the convolution. So this is the sum of x plus y, x and y, and the density of z is the convolution of the PDF of the sum of x and y is the convolution of x and y. That's what we stopped at. So now I'll try and do an example. I'll give an example. Just get this back to 100%. Very good. Excellent. Let me do an example. An example 5.5.3. So let's say let lambda be positive. Let's say I take x to be exponential lambda 1, lambda. And let's say y is also exponential lambda. Y is also exponential lambda. That's 10 now. Depends on let's see. Okay, I'll take a little bit of work. We'll see if this works. Let's start again. Okay, it's back on. So here the idea is that x is exponential, also lambda, and they're independent. So and independent. So x and y are independent random variables with parameter lambda. So now let's say again I say let z equal to x plus 1. Now how do I find the density of z now? So now I know that the density of x is equal to, so let's go step by step. So you know the PDF of, so now I want to use this theorem. I want to use the theorem that density of z is going to be given by the convolution of density of x and y. So now I know density of x is given by lambda e to the minus lambda x, then x is positive, and 0 other 1. That's the density of x. I also know the density of y at the point y is the same, lambda e to the minus lambda y, then y is positive, and 0 other 1. Right? So then the density of z we know from theorem is going to be equal to, let's go theorem down. Let's write this down. The density of z we know from the theorem is that is the integral of minus to infinity f sub x at the point x, f sub y at the point z minus x dx. Right? So this is z. This is all density. So what's that going to be now? That's going to be equal to, so just write it down. This is equal to, what's it going to be now? Minus to infinity. The density of x is just going to be just lambda e to the minus lambda x. Only when x is positive, right? So that means, so you should just observe a little bit that this thing is going to be, this person right here, let's write it down, is going to be lambda e to the minus lambda x only when x is positive, right? Otherwise, it's 0. The density is 0. It's going to go fat. So what you do is you write this down as minus 0 to infinity, first step. F sub x at x is just lambda e to the minus lambda x. And this we leave as it is. F sub y at z minus x dx. But we know that this person right here, right, is going to be lambda e to the minus lambda times z minus x only when z minus x is positive. Right? Let me edit this. That means x is less than z. That is, x is less than z. Right? So that means this person right here is going to be just equal to 0 to infinity lambda e to the minus lambda x. This person here is lambda e to the minus lambda of z minus x. Minus x, so black here, of z minus x dx. That's what I get. So if I do this integral a little bit carefully, what do I get? I just get lambda squared e to the minus lambda, and this z comes out, right? So it's z minus x. So only z is positive, so it's go till z. Otherwise, x. So I need this is what I told you. X is less than z. Right? So it's going to be this. So that's going to be equal to. So all I get, the x cancels off, and I get 0 to z of dx. Right? And that's just going to be again z here. So z. So I have f sub z at the point little z is equal to this guy, which is now what is going to be equal to lambda squared e to the minus lambda. Right? And then I have z, then I have another z. And this is true only if z is positive. True if z is not negative. And it's 0 otherwise. And f is easy to check that f sub z at the point z is 0 otherwise. And the idea is because of here, right? Because this, I need here x positive, I need an x positive, and I need here x less than z. But x is positive and x is less than z means z has to be positive for this whole calculation. So let me just recap this calculation. So I wanted to use this theorem that said that if I have the sum of two random variables, independent variables, the density is given by the convolution. So I took sum of two exponentials, and it turned out that f sub z looks like this in this form. So this is not exponential. So sum of two exponentials is not exponential. Important to keep in mind. If you recall what we did with Poisson, for example, with Poisson, sum of two Poisson became a Poisson, but sum of two exponentials is not exponential. So this would imply that this is that means first z is not exponential. So then this whole thing it's a family of distributions called gamma distributions. So I'll state the definition down, and then they all come with a family of a distribution called gamma. So this is a definition. 5.5.5. So x is gamma n lambda, where lambda is positive and n is the natural number. If its PDF is given by f sub x at the point x is going to be lambda power n by n minus 1 factorial x power n minus 1 e to the minus lambda x when x is not negative. So lambda is typically called the shape parameter, and or sorry, lambda is the rate parameter, n is the shape. So n is the shape and lambda. So n is the shape and lambda is the rate. It's essentially because of the plots, right? So if you look at you just try to plot the density of x. So we'll do this way, and zero otherwise, right? Zero otherwise. It's only true. So we erase this. Okay, before I do the plot, I'll just come and say above example z was gamma 2 lambda. So if you sum two exponentials, you get gamma. So that's one observation. So I write observations separately. I write neatly. And we erase this whole thing. This definition of gamma. So first thing you observe is that these observations. Let me do marks. If n is equal to 1, x essentially is like gamma 1 lambda. And if you stare a little bit at it, so this is again, I have 0 otherwise. Stare a little bit, that's the same as exponential lambda. If x is 1, n is 1, the x disappears and you just get exponential. So if n is equal to 2, then you observe that let's take, in our example, z was essentially gamma of 2 lambda. And that we know came about by summing up x plus y, where each x was exponential. So sum of independent exponentials give rise to gamma. So it's an exercise to check that if I take x1, x2, xn, all independent exponentials of lambda, then if I take z sub n to be the sum from I equal to 1 to n x sub I, then this should give you Zn should be distributed as gamma of n lambda. This is something you can check by induction. Okay, so that's about sums of random variables. Just one small fact about gamma, and I'll close the discussion, is the idea that if you plot the gamma density, right? So, for example, if you look at the x-axis and the y-axis, I'm plotting, let's say, x is gamma of, let's say, n gamma lambda, right? I'm trying to plot the density, right? So now, let's say if n was equal to 1, let me draw n equal to 1, then at the exponential random variable, that just starts at just lambda e to the minus lambda x. So when x is 0, this is the value of x, let's say this is the value of x. When x is 0, it just comes down. It's 0 to here, and then it just starts here, and then lambda, some lambda, and then this comes down. These are the Then let's say for n equal to, let's say, 2, that is, so here you'll have, let me draw different color perhaps, maybe brown. Let's say n equal to 2. So n is equal to 2. That means I have lambda x to the minus lambda. So it just go up and come down. You start like this, and then you come down. Maybe it'll come down a bit. It'll cross this guy. So you start this guy and you go down, then come down. This is our gamma 2 lambda. And then if you do a little bit further, it'll go more and more flat. Let's say I do, let's say, gamma, let's say, let me do purple perhaps. Let's say n equal to 4. I mean, it's a more flatter curve, so it'll just sort of start a little bit further ahead. It'll keep going a little bit slower and then climb up to this. And then. So this would be like lambda x to the 3 e to the minus lambda x by 3 factorial. That's what you get. That's what this looks like. So that's why n is called the shape parameter and lambda is the rate parameter. It's a plot of f sub x. Oh, very good. So gamma is kind of useful statistically and in physics quite a bit. Models many things. So now let's do another simple calculation. Let's do a quotient calculation. So let me go back here. So let's say suppose x and y are, this finishes this topic. Suppose x and y are two independent random variables. Very good. Right. And with model density is given by f sub x at the point r to r, and let's say non-negative of course, and f sub y is also from r to r also. And then I'm a little careful. So let's say suppose the probability of y equal to 0 is 0. So I can look at x equal to z equal to x by y. I take two independent variables, this density x by y. So then I ask the same question: what is the density of x? What is the PDF of z? So how do I get that? Again, I do the same thing. So I do so. Let's try this. So here I do step 1. I get it before. I go and find the distribution function of z. So I go again. I do f sub z at the point z is equal to probability of z less than equal to z. So that's the same as the chance that x by y is less than equal to z. So what's that going to be now? That's the same as, so again the region you have to be careful. Again, x is the same as probability that x is less than equal to y times z. So this I won't draw the graph region. So this is just y times z. Z is here. Z is here. So all you have to do is you just have to integrate out the joint density, right? So again, same as you integrate out. Let's say minus infinity to infinity. So let me block here. Infinity to infinity, right? Of not of the region, right? So the region is not this. I won't do this. So I do this. So instead of all x comma y, for which x is less than equal to y times the value of again f of xy, but f of xy we know is f sub x at x times f sub y at y dx dx. So now you have to be a little bit careful. So now if so again this is not quite right. So what I wrote down here. So let me just backtrack a little bit. This is not quite right. I'm sorry about that. This is not quite right. This is only true if y is positive. So let me scratch it out. Let me come back here and leave that as x by y. X by y is less than. So now, of course, now, and then I assume that y is not equal to 0. That is, because y equal to 0 is just one single point, I can ignore that. So now, if you just do a simple calculation, just do the algebra properly, you will get this equal to, so you get this double integral when x and y, right? When x is less than or equal to y times z, and y is positive, right? It's y times z. When y is positive, plus the integral, so the integral of x comma y, x less than or equal to, x is bigger than y times z, y times z when y is negative. And that's how the region will split up. And inside you even have the same thing, f sub x, x, f sub y, y, dy. So I just copy again, duplicate. That's why. This, if you just stay a little bit, you're just going to get it as, if you just work a little bit harder, it's just going to be minus infinity, infinity. On the one hand, you'll get, on this hand, you'll get minus infinity to, or here to y times z. And that's how x goes, to y times z of the same thing. I put this guy here, duplicate again, here. And that's what I get in inside. Plus, here I'll get minus infinity, or I should not say y, it's negative, right? So y is negative, so y is positive. So here y is positive. So here I should get the reverse, right? Here's y is negative, and then, so maybe I'll just write it properly. Here y is positive, so this a little bit. So y is positive, so 0 to infinity, and x goes from minus like z, and here I go from minus to 0, y is negative, and I go from yz to infinity of f sub x at x, f sub y at y, dx. That's right. Right. Very good. So now all I do is, once I have this, if I have to be a little bit careful. So when I do this differentiating in z, so that I leave the expression as this distributed function of z. So the density function of z, that's step 2, the differentiating f sub z at z, which is the derivative of the distribution function. I'll leave that as an exercise for you to check that if you differentiate the above guy, you'll end up getting this will be equal to minus infinity to z. So you put the z in red. So f sub z at the point z is equal to minus infinity to z. This time it won't be a convolution. So minus below z. So minus infinity. And I'll have a mod, I'll do y, this time in x, f sub x at the point z times y, and then f sub y at the point y. This will require some work. You'll have to differentiate the top guy to get this. But that's a calculus exercise. That's a calculus exercise. So this also has sort of very illustrative idea. That is, one can check that on to simple calculations. Let's do a simple example. Let me see if I can start that and finish it. Okay. So this distribution you've seen come before, but we'll try and see how to get it from ratios of two normals. Let's say x plus y for 9. So let's say x is normal with mean 0 and variance sigma squared, let's say, or variance 1, let's say. And let's say y also is normal with mean 0 and variance 1. Let's say they're both independent. And let's say z is x plus y, so x by y. X by y. How do I find the density of z? Right? So now here's the idea that I go here. So I know the same formula. I know the formula is this. Right? So I know the formula is f sub z at the point z is equal to. Let me copy this formula down. Duplicate it. Let me bring it down. I go back here, I'll write it down. So f sub z at the point z is given by this formula right here. Right? But we know that the normal density is just e to the minus x squared by 2, right? So I have minus infinity mod y, I'll have e to the minus, here I'll have minus z squared, y squared by 2, e to the minus y squared by 2, and I have a root 2 pi here, and I have a root 2 pi here, dy. And what's that going to be? That's going to be equal to, sorry, that's going to be equal to, minus infinity mod y. So if I add these two things up, I just get over 2 pi, and I e to the minus, this is just z squared plus 1 is a constant, right? So I just get z squared plus 1 by 2 times y squared. Right? That's what I add dy. This is what I end up with. So now you'll have to learn to evaluate that. So that's going to be, if you just think a little bit, this is just an even function. So this is going to be equal to, so twice. So it's going to be 1 over pi, 0 to infinity. So it's going to be twice of this guy, the 2 cancels off, so 0 to infinity, of y, e to the minus, I have the z squared plus 1 by 2 y squared dy. And that, if you just do a little bit of algebra, right, it's just going to be, just say, let's say you change a variable, let's say u is equal to, z squared plus 1, that's a constant, so it comes outside, so z squared plus 1 by 2 times y squared. You change a variable, or use substitution. So what do you get? This is going to be equal to 1 over pi of 1 plus z squared. 2 is going to cancel off. It's going to get to the 2y. I get this outside, and then inside I get 0 to infinity. Right? I just get e to the minus u. That I know is just 1. So that's going to be equal to 1 over pi of 1. So what I've got, f sub z at the point z is equal to this times 1 plus z squared. So minus infinity less than z. So we have seen this before. I don't know if you recall. This is just z is just a Cauchy with parameter 1. So essentially, the ratio of two normals, it gives you Cauchy distribution. So probability has a lot of nice interplay like this. So distributions arise naturally from functions that are variable, and one can play with these distributions to get very interesting examples. So I'll illustrate more on the homework assignments about how functions work. The next one, not this one. Okay, very nice. So this sort of sums up. So two things we did today. We did sum the random variables and quotient random variables. And we also understood how to compute contingent densities on this.